just record this. Let me just see. Okay. So these are the pack. You know very well you are already popular with these two packages, and also you are popular with these two data visualization packages. And this one is sklearn, the sklearn. It is also called as scikit-learn. So this is the package we use it to train our machine learning models. Okay. In sklearn, we have a submodule called linear model. So from this, we are importing linear regression class. It's a class. In the OOPS concept, there is something called class. Okay, at this moment, let's not worry about class and all the things. Okay, this is a linear regression. We imported it from this submodule because we wanted to fit a linear regression model. Okay, for this, we need to have a class to import it from a model. Okay, so that is available here already. Someone has already developed everything. All we need to just simply import it and then play around with it. That's all. Okay. Next one is, this is the data set, housing data set. Let's say you are working for a realtor, so a real estate, okay, company, and they are expecting you to predict the target outcome variable, which is nothing but the price, housing price. So in that case, what will happen is, right, we need to know, in the given data set, which how many number of features are there. Here we have 4 features are there: size, UDS, park, and MISC. What do you mean by features? These are the input variables. This is what the output variable. Let's say your manager has given you all this information, input as well as the output. So you have 4 input features and 1 output variable. Everything is available here. Cool. And in this case, what happens is, this data set, we want to understand how many number of records are there in total. For that, see, my data frame name is SDF. SDF of shape, if I give, it gives me how many number of rows are there in this data set, how many number of columns are there in total in this data set. That is what we can see it here. Got it? That is what we are able. This is what we discussed. And next one is, we want to check all these 4 independent variables or the features, the input features, how well are they correlated with the target outcome variable called price, because we want to predict the housing price. In the case of linear regression model, in the case of regression problem, especially when it comes to linear regression model, okay, each and every, the input features or input variable should be correlated with your target variable called price. So in the y-axis, I have plotted the price. We have a plot called, we have a function called pair plot that is available as part of SNS package. And with this pair plot, we can plot more than one chart. Okay, we can see 4 chart here, the size and price. Look here, the x-axis. One second, the x-axis, I have plotted the size in this chart, and UDS x-axis I plotted it, and park x-axis I plotted it, MISC we plotted in the x-axis, and the price is the one I plotted in y-axis, because this is the one we want to predict it. So all these independent variables, 4 independent variable, must correlate with the target outcome variable. In case if there are no correlation, any any correlation exists between the input and the output variable, those variables are not helpful in including in your model, while importantly while training your model. Okay, so in this case, look here, this is this is the one visually we are checking it. When you visually look at it, sometimes you may biased, so better you can use heat map. In this case, your data frame is hdf.core function, and here what we are doing is sns.heatmap. Okay, the heat map is a function. Here I just directly specify hdf.core function. This is the one gives me the correlation. How many of you remember we discussed about correlation? What notation needs to be used for correlation? R, right? The correlation R should ranges between -1 +1. Any value which is very close to 1, that means there is a high correlation exists between the 2 variables. So this line of code, what it does is it creates a chart. Okay, in this case, you can look at only this row here. Look at only this row, price, and here you can see the only the independent variables or the input features. You can see it here. Rest you can see price and price. If you try to compare price, something like we are comparing ourselves with ourselves. If you compare yourself with yourself, you always think you are perfect, right? So hence, see, in this case, so price and price, if you look at it diagonally, right, all the values are 1, 1, 1. So if you compare the same variable with itself, it will give you 1. Hence, it doesn't make sense. Okay, you need to compare the each independent variable with the target variable called price. This is what we want to predict. So if you look at your price and size, the independent variable size and price, the correlation value is 0.8. So which means the 0.8 is somewhat low, +1 or 1. Hence, there exists a correlation, good, or strong correlation exists between size and price. See, it's something like, husband, wife in a family, a simple analogy. Husband, wife, are they really having so husband, wife is a relationship, right? Husband, wife relationship is there. How strong the relationship? How strong the relationship? If it is point anywhere, one, anywhere close to one, that means the relationship is. So is there any way we can quantify the relationship? That is where the correlation is coming into picture. With this simple analogy, you might be able to understand, right? So husband, wife, they are living together. Are they really happy? Are there any correlation? Are there any stronger relationship exists between husband and wife, right? If the relationship is weak, there could be chance they may get separated, right? Okay, that's how. Okay, so in the you just think relate that analogy with this one. The size and price, there exists a relationship between these two variables, but it is 0.8, which means stronger relationship. There exists a stronger relationship exists between these independent variable, this dependent variable, and similarly UDS, undivided share. This is 0.56, which is somewhat, if you round it off, this one you will get 0.60. 0.60 is also somewhat closer to 1. Hence, we can see it's, there is a correlation, but Park and MIS, if you see 0.2 is nowhere closer to 1, right? It is a weak relationship. There is a weak relationship between Park and price, MIS and price. Hence, these two variables are not helpful in terms of predicting the target outcome variable price. So in my model, ideally, we have to use size and UDS as an input variable or the feature to predict my housing price. What we are doing is first start with including all the input features blindly. Okay. Here, I'm using two variables, x, y. The x is the variable which is holding all the four independent variables or the features in it. Okay, SDF features, if I give, this is a list. You remember, it's a list, right? Feature is holding this list. We pass this list as an argument. The SDF, it's a data frame. So in this data frame, what we are saying is, hey, use these four columns only from this SDF data frame. And then we are something else called Y. And in the SDF data frame, we are going to use price directly. This Y variable is holding the dependent variable. This X variable is holding all the independent variables. Okay, got it? Yes. So that is what I'm printing and checking it. Print X. Yes, only four independent variables. Here, dependent variable, we removed it, right? Logically, we removed it. Now, now the question is why we need to create X and Y, because there should be a clear distinction, right? So X is nothing but all independent variables. Y is only your dependent variable. So in this case, we are fitting a multiple linear regression model. What is multiple linear regression? Already we discussed, right? So you have more than one independent variable. So far we discussed about housing price as a dependent variable and size of the house is an independent variable, right? So in that case, we call that one as a simple linear regression. If you are using more than one independent variable, that is called a multiple linear regression. Okay, now what I do is I'm going to train my linear regression model. Okay, here I'm going to initialize the linear regression class. Okay, I'm creating an object here, init_fit. So, right, so here we are simply initializing. So you remember the linear regression which I imported just above here. That is the one I'm initializing it here. So now what happens, the init_fit is holding this, this pointing to this one. Init_fit method. Method is kind of function, okay? We are passing all the independent variables and dependent variables. Okay, here I just skipped one line here. 1 second, where is that? Train test split. Yeah, this is the one I just made it. Okay, it's not marked down. Actually, it's a code. Okay. Yeah, this step I skipped it. See, when it comes to any machine learning model or including deep learning model, you need to split your data set into training and test data set. Okay, training and test data set. So using train test split method, which is available in this submodule, I'm going to import it. The same thing I'm going to use it here, train test split. Here you remember already we created X and Y. So here I'm passing X as first argument, Y as second argument, random state equal to 100. So this is the one is something like produce the same test result, even if you execute this code snippet multiple times, produce the same sample data. Okay. So train test split, what happens is, oh, sorry guys, there is some net problem here. Okay, here the train test split. The train test split function, what it does is, it takes the X as an input variable. X is holding all the independent variables. Y is holding only the dependent variable. At this one, you forget about this. Okay, we'll discuss it later. Okay. So the whole idea here is, if you simply give X comma Y, what this function does is, it splits your all this data, the independent variables related data, and as a 75% of data. It randomly splits your entire data as a 75%. It randomly samples 75% of your given data as a training data set. Okay, remaining 25% will be used as a test data set. Okay, so here if you see here, the output of this one gets stored on the left side. X train, X test, Y train, Y test. Initially it might get confused. Since you are new one to this, you can watch my video more than one time. Guys, please bear with me. Okay, tomorrow morning everything will get uploaded. Okay, as of today. So here in the X train, right, so in the X train, what will happen? The 75% of this randomly sampled data set for these input variables will get stored here. And Y train, what will happen is, the 75% of randomly sampled dependent variable value will get stored here. So the price, okay, the price, 75% of the price data gets stored here. And then X test and Y test. So here 25% of all these independent variables data gets stored here. And Y test will hold the 25% of your price related data into this one. Okay. So we have train and test related data. You just think about it. Okay. Don't think too much. Okay. What did we do so far? We just explored the data and then we created two variable X, Y, and then we created the train and test split. What we are doing is, we are creating training data and test data. Training data is holding 75% of the data by default. The remaining 20% data will be used for test purpose. That's all. Okay, 75-25 ratio. That is the one I just checked it. X train, how much percent? So in total, we have how many number of records? How many of you remember 148 records, right? In total, we have 148 records. Out of 148 records, 75% is how much? Can someone tell me? 75% of 148 records, how much? Yes, Soundarya and Raji, you are correct. So almost 111, right? 111. So this function did a good job. It automatically splitted my entire data, as a training data, with 75% of the data. Okay, or 111, which is 111. Remaining 20% data is there in this test data set. So X train, X test holding all the 4 independent variables only, but the X train is holding 75% of the sampled data, randomly sampled data. X test is holding the 25% of test data in it. Okay. So next, yes, Soundarya. So the Y train is holding 75% of the price, the dependent variable value. Y test is holding remaining 25% of data for your price. Okay, good. So we have splitted the training and test data set. And the next one is, we are training the linear regression model. And here I have initialized this class linear regression. And the output of this one gets stored here. Now I'm going to use this one init fit dot fit method. Using fit method, We are training our model. So here the X-train is holding how much? What does it holds here? How much? Can you all please type it in chat? What does it holds here? The X-train is holding 75. Yes, you are correct. Soundarya, you are correct. And the Y train, sorry, the Y train also contains 75%. Okay, 75% of independent variables. And 75% of dependent variable values. Here also the variables values. Okay. So all the four variables, okay, the independent variables, here dependent variables, 75%. So these are related to training data set. Okay. And we need to tell this fit method, which variable consists of all the independent variables, X train, which variable consists of the dependent variable, the Y train. Okay. So we are done. So, and if you execute this, and when you execute model, so now your model is ready. We trained our model. My model name is model. Okay. Now in the model, we have something coef underscore is available. This is nothing but the slope for all the independent variables. Slope for all the independent variables. So your what is your first independent variable? The size, right? Size, UDS, park, MASC. For each independent variable, it gives me the slope. Okay, it gives me the slope for all the four independent variables. If you want to see the intercept value, this is the intercept value. So as I told you, in the case of multiple linear regression model, each independent variable has its own slope. Okay, the slope is not common for all the independent variables. Okay, the slope is independent of all the input variables or the independent variables, whereas the input is common. Okay, so now as I told you in the past session, the slope we don't have to calculate, the intercept we don't have to calculate. It is automatic. You can get it automatically from this one. Okay, from the model. And next one is, see, now my model is ready. Great, my linear regression model is there. Our manager gave me the data. So I splitted the data into training and test data set. The training data set, I used it to train my linear regression model. My model is now my model got trained with 75% of the training data set. Good. Now I need to check how my model is performing. See, if somebody says, let's say somebody gave you the data, they want you to take the data as a base version to train your model. Now your manager gives you some other data. Okay, I gave you the data. You said you trained your model. Your model was ready. Model name is model here. Okay. So why don't you apply this trained model on the unseen data? Now I will give you some other data. But in this data, I will not give you the price. I don't know the price. With the previous data, with this historical data, okay, we have trained the model. Okay, my model name is model. This is nothing but my linear regression model. So now I need to apply this model on the unseen data. Now my manager gives me another set of data wherein I don't have the target variable called price. This time, hey, you see, previously he gave me the price also, right? So look here, in this case, he gave me the price also. This time, this is your training data set, okay? Next time, what he does, he gives you some other data. For this data, I don't have the price. I have only the input variables. If I, give me the estimated housing price. So what you do is predict, you apply the model on the unseen data, okay, new data. Model dot predict. There is a function called or method called predict. Then the argument is X test. This is your unseen data. That's how we splitted the data, right? X train is for training data set. X test is for test data set. But we have trained this model linear. Airtel is such an horrible service, man. Okay. So now we need to apply the model on the unseen data called X underscore test, model dot predict X underscore test. Okay. So now what happens? This predicted value for the new data set given by your manager gets stored in your predict. And if you want to see the predicted value for the unseen data, model predicted for this. Now the model predicted the housing price for the unseen data that got stored here. Pred. If you give this is the one, you can see it here. So this is the one for each and every record in your X-test data set, right? The model predicted. Got it? Something like same thing. So let's say, you are taking 5 toys, 5 camels, but different, sizes of the camels. Okay. What you are doing is out of the 5 camels, you show only the 3 camels to your, okay. Again, the problem here, net connection problem. Please bear with me. Okay. And here, yes, see, out of the 5 toys, what you are doing is you are showing only 3 toys to the kid, but all the 5 toys are related to camel. Okay, when you show the 3 toys, the camel red toys, right, the kid sees and different, but each camel toy is slightly different in the color and the height and all. Okay, but the shape is same. And what you are doing is, okay, you teach the kid, hey, this is a camel, camel, camel. All the 3 toys you tell, the kid can understand. Okay, afterwards, to check whether the kid has understood very clearly or not, you are showing the remaining 2 out of 5. You show the remaining 2, which you never show it to your kid, right? So, and this time when you ask the kid, right, the kid should tell very clearly, yes, this is also camel. That means the kid was able to memorize. The kid was not memorize the thing. It was able to generalize its understanding. So it was able to learn the pattern. When it sees the new toy, it applies the pattern. Whether the neck of the animal is taller, yes, it is a camel. Same principle here it is applied. So first train the model, apply the train model on the unseen data, which is nothing but the test data set. So now the question is, okay, your manager asking, okay, you gave me the predicted or estimated housing price with your trained model. Fine. So how accurate this one? How can I rely on this one? So how accurate your model predicted? Can you give me something like that? So in that case, how will you evaluate your model? So that this is called cross validation using the test data set. We have applied the model, right? Now we have some metrics using which we can we can evaluate the model performance. Okay. So how do we evaluate the model performance? We have something called mean squared error. You remember, we add all the errors. Before we adding all the errors, we need to square the error and we need to add it. That is what we discussed, sum of squared error. Okay. Instead of taking sum of squared, mean squared error. We have something called mean squared error. So now what I do is to evaluate the model, evaluating model performance for training and test data set. I'm going to see root mean squared error. Okay, we are taking the square root on the mean squared error. That is what your root mean squared error. So we have something called square root function that is available as part of NumPy package. And now what I am going to do is I'm going to use something called matrix dot mean squared error. It's something like, somebody gives you some task and you go back and tell them, I have completed, sir. Now the next question what there is, how correctly you did this job? Can you justify? The same thing we are doing now. Now we created the model, we trained the model, and then we applied the model on the unseen data. Now we are going to test how accurate these predicted values. For that, we are using something called mean squared error. Okay. So here I'm going to say y train, and okay, here I'm going to say y train underscore predict function. Instead, I just say the predicted values. Okay, the pred. RMSC. Lesser the error, better the model accuracy. That is what we discussed as part of the theory. What is error? All of you, please type it in the chat window. What is your understanding about error? How many of you were able to? Yes, you are correct, Raji. Raji, correct. Soundarya, correct. How about others? What is error? What is error? How many of you remember it? Guys, don't mess up your life. It is your, don't be content with what you are doing. Okay, what you are doing is just for save your life. That's all. If you want to mess up your life, you're gone. So please revise the topics, whatever it is. Okay, don't say, I don't have the video, but previous batch videos are, it's there, right? 1 second, I just executed this one. There is a series of net connection problem. 1 second. Others thought the session was over. Okay, let me, matrix is not defined. Let me go down here, matrix dot means code error. Okay, let me do one thing. I will just put it here. Okay, I'll do one thing from or import this one thread is not defined. Okay, let me do one thing. I need to redo everything. Not necessarily everything, only this one is enough. Thread, and you can also do this way. Actually, I am explaining you in a very simplified, version of this one. Only thing is you need to practice it. Okay, 11. Okay, y train and okay, square error. Okay, here I need to use the test data set. See 2.047. This is not my error. So lesser the error, better the model. So all of you know, right? What is an error? The actual and predicted value. Difference between obtained value and collected value. Obtained value and not the collected value. See, difference between the actual value and then the predicted value. The pred, right? Predict function predicts the output. Okay, this is the one. So how about yes, most of you answered it correctly. There are few of you, you have not answered. That means, you are not doing hard work. Miracle will not happen unless we work hard. Okay, let me do one thing. Y underscore train dot predict. Okay, this is RMSC one. Let me just check. Okay. Here, okay, here I'm just trying to find out the error for the training data set. Okay. And here, what I am going to do is, okay, here I do a simple thing here. Here, what we will do is, model dot predict on the training data set. So right, say train model dot predict. This I am going to say pred one. Okay, pred one. So what we will do is next week we will work together. I will give you some data set. We will do it parallelly. Okay. So that will be. If you see here, look here, I will use the training data set. The training data set, the target value, price, the actual value, and then predicted value. The predicted value, in this case, I'm using I'm applying the model on the training data set itself to make a prediction. Okay. And the predicted output for the training data set stored in pred one and this one I stored in RMSE1. Okay, so this one. So now the point is the test data. With the test data, what is the error? When I apply the model on the test data set, unseen data, how much, what is the error I'm getting it? But when I apply my model on the training data set, how much? It's 1.60, close to this one. So there is a difference between these two, error. Okay, ideally, the test error and then the training error should be somewhat closer. If the difference is too much, that means my model is, let's say my training error is very less, but my test data error is little more. That means my model was not generalized well. It's somewhat memorized. Okay, somewhat memorized. Okay, what we will do is, in this case, we need to fit a model again. In that case, you remove these two one, because these two variables, as I told you, Park and MISC independent variables are not correlated well with your target variable price. But still, we have included these two independent variables, because of which it can introduce some kind of random noise. That random noise can cause error. Okay, so what the other hello, am I audible to all? So okay, the training error, this is what my training error, model training error. This is what my model test error, test data set error. When I applied the model on the unseen data, or the this is the one is, we applied the model on the seen data itself. Okay, why should I apply the model on the training data set itself again? Because you wanted to know how well my model performs with my training data set, how well my model performs with my test data set. If the error is somewhat close by, then my model generalized very well. Otherwise, my model is not predicting well. Okay, and now using root mean squared error, we are able to evaluate how well my model is doing it. It's something like car is, let's say you have manufactured a car, right? You are owning a car company. You are owning a car company. You are manufacturing a car company, and customers ordered 10 cars. You produce 10 cars. Okay, you produce 10 cars, fine, but you need to do a test run, right? Whether the car is running correctly or not, with all the first gear, second gear, third gear, fourth gear, right? Okay, car is running fine. Everything alignment, wheel alignment, everything is good. All the features are working fine. Okay, good. But how will you evaluate your car is compared to your competitors' car? Your car is far better. Mileage. We use a mileage, right? Using, so if you say your customer, hey, car is ready, man, you order, you take it. You think he will take it directly? No, right? You will test it. You will take a, you will, he does a test run, and then he checks the mileage. That is, mileage is kind of a metrics. Okay. So if my car gives me, within the city limit, 15 kilometers per liter, that means good with AC, and within the city, 13 or 15 kilometers per liter mileage, then it is good, right? So using mileage, we are going to evaluate how well your model is, your car is doing. Similarly, once you create a model, you need to test it, right? How do you make sure that your model accuracy is good? That's where we use our root mean squared error. Okay, root mean squared error. So root mean squared error. In this case, we are taking the mean on the error, squared error. We are taking the mean on the squared error, and then we are taking the square root on that one. That is why we call it root mean squared error. This is the metric we use it to evaluate how well my model is performing. For that, we are applying the model on the test data set. We are applying the model on the training data set and then we are finding out the mean squared error for both. And then we can see that the mean squared error is somewhat closer, but it is little difference is there, right? So that means my model is not generalized well. my model is not generalized well. So what can you do? So this is where as a data scientist, we need to do some kind of fine tuning. Probably the next step is we will remove these two variables, and then we will check after removing this one, again you need to do the same thing. Okay, train and test data split. Okay, so in that case, you need to train the model. Everything, all the steps you need to carry out again. See, this one, what I would suggest is I'm going to include a new cell. You just copy paste it here. In this case, you need to, this is an exercise for you all. Next week, you all going to do with me, along with me, okay? And here, that's all. Again, you need to train this one. Execute this one. That's all, very simple. Once you build it, next copy paste, that's all, right? And here, yeah, what I am going to do is I'm going to run this one 2.03. Now you see it got reduced slightly, but still it is there. There is a slight difference. Let it be there. Maybe the data what we are using it not sufficient enough. Okay, maybe in that case you can ask the customer to give some more data or generate some more data. Okay, what you do is here you can go and play around with this train and test split. As I told you, where is the train and test split? Train and test split, it is there here. By default, it gives me 75-25% of split. How do I override that? Test size is equivalent to 0.30. In that case, my training data set will have 70% of the data instead of 75, and test data will have 30% of data instead of 25% of the data. Okay. And here I'm going to do this one. I just do this. Now, still the error is going up. Maybe, right? We will try with 40%, 40, 60. Okay, 40% is your training data set. But ideally, your training test data set should be more. What I will do is, in this case, the overall record itself less. I'm going to use 20%. Remember that. So to train your model, the training data should be more. Okay. And here it gives me 1.58. Same thing, we are seeing it here. Let me do one thing. I will just hit it again. Okay, here the model dot predict. Red one already I stored it. 1.56, right? So the previous one itself good. So with 75-25, it was coming down, right? So 2.20 with the test data set, we will go by with 25%. That one itself an optimal one. I'm going to fit the model again, and I'm going to train the model. I'm going to predict the model, and I'm going to find out the difference between actual and predicted for the training data set, and actual and predicted difference, for the test data. Now it got reduced 2.03. It's fine, kind of okay. So now the question is, yes, as what's your name? Soundarya, right? As she typed in the chat window, for different training and test data set, the error is changing it. How can I make sure that my model is, performing consistently? Okay. Yeah, and that's a very good question from Soundarya. I just repeat one more time. Her question is, if I cannot keep split by keep changing the training and test data set split 75% for training test data set. If I use 25, the error for the training and test data keep changing it. In that case, what ratio can I use it? How can I rely on this test split? That is what I will. So yeah, in this case, what you do is we have something called 10-fold cross validation. With the 10-fold cross validation, we are going to take a call whether this model error is consistent or too much a variance is there. I will give you one simple story to understand k-fold cross validation. It's something like if somebody is asking you, hey, what is the review of that movie? Like, let's the Leo movie. What is the review? What is your feedback? And if you ask one or two people, they will say great, right? Or what you do is they may say that movie is not good. Okay. Instead of asking two people, if you ask 10 people, you will get unbiased response, isn't it? 10 different people randomly you call them, and then you ask them. If there is a too much of variation, let's say out of 10 people, 6 people or 7 people say, hey, that movie is good. then you will be confident. Yeah, that movie is good. It's worthwhile spending money going to the movie and watching in a theater, right? Got it? Out of 10, 7 people, if they say that movie is good, then you are going by them, right? You go and watch the movie. Otherwise, you are not going to. Likewise, in the 10, using tenfold cross validation, what we are doing is we are creating different training and test split. In each train and test split, what is the accuracy? Okay, what is the error? If the error is consistently with the training and test split, if the error is somewhat close by, we need, right? So what we are going to do is, yes, we don't see any variance too much. Too much of variance is not there. Whereas the error is slightly more, it is okay, but the variance is not much. If the variance is too much, see you are asking the 10 different people about the movie with rating, right? The people, one person give one rating. Well, it's 0 to 5, one being top rating. You just think that way, okay? One being top rating. So one and a super movie is really good, okay? So you 0 to 5 there is the scale, and out of 10 people, and 7 people they give somewhat close to 1, right? If you take the standard deviation, it gives you less, right? The variation is less. If different people give different, one person says rating 1, some one person says rating is 5, and some person says rating 3, for too much of variation is there, that means your model is not performing consistently well. You may need to include additional features, or you may need to drop some variables that are not helpful in terms of predicting your model. Okay, to make it simple, train the model, apply the train model on the unseen data, that is called cross validation. And okay, we applied the model. Now the question is, how do I make sure that my model is performing well? We use a metric called root mean squared error. Using root mean squared error, we are going to compare the training and test data set model performance. When my model, how well my model performs with the training data set, what is the error? 2.03. How well my model performs with it unseen data? The error is 1.58. So, if you see 1.60, somewhat close by, in real time scenario, it will not be, exactly close. Somewhat close is okay. Okay, somewhat it is close. Okay, fine. What is the next step? Next step is the cross-fold variation. To answer to the Soundria's question, that is a real-time based question. In the real world scenario, they'll ask you, how will you make sure that your model is consistently performing well with across different train and test data sets? For that, we do the k-fold cross validation, which we'll discuss it a little later. Okay, because I don't want to overwhelm you by discussing so many things in a single session. Next one is the important thing is the regression, the assumptions. What are the assumptions that needs to be validated? Okay, but unfortunately, with the sklearn package, you cannot validate all the assumptions. First of all, what do you mean by assumptions? You remember in the case of hypothesis test, one sample t test, one sample z test. In that case, the assumption, what are in the two independent sample t-test? What are the assumption in the case of two independent sample t-test? The samples should be independent of each other, right? It should not dependent on each other. That is one of the assumption. Similarly, when it comes to linear regression model, not only you evaluate the model with the metrics like root mean squared error, in addition to that, you need to evaluate your model with the regression related assumption. There are 5 types of assumptions. It's something like you go and check your heart rate. Let's say you have a chest pain. You go and check your heart rate. Heart rate should be anywhere between 70 to 100. That means you are safe. Maybe you have musculoskeletal pain, not the heart pain. Okay, your heart rate is 70 to 100, fine. And your blood pressure they check, right? Your blood pressure is also normal, 120/80, somewhere between 120 to 80. Your blood pressure is good. Heart rate is, almost, your heart rate is 80 or 83, you are good. That doesn't mean you are good, right? Heart rate is good, the blood pressure is good. That doesn't mean you're always good. Still, there might be chances you have some stones in your kidney, right? Kidney stones, or because of which it got infected, due to which you have some kind of discomfort, and that led to some kind of mild chest pain, right? It would have increased your blood pressure also. Labile blood pressure. Sometimes your BP will be normal, sometimes your BP will be abnormal. Okay, that is called labile blood pressure. So similarly, not only we rely on heart rate and blood pressure, there are other parameters also we need to check to make sure that you are really healthy, right? Right, when it comes to the linear regression model, the same thing is applicable. Okay, somewhat. Okay, root mean square alone not sufficient. In addition to that, whether your regression fitted model or trained model meets the 5 assumptions. One is the linearity, and number two is independence. Number 3 is homoscedasticity. Good, Soundarya, you have gone through all my videos. Okay, very good, very good. Fine. You are typing it. Okay. Okay. No or little multicollinearity. So these are the 5 assumptions. That's all right. Only 5 assumptions, not much. Your model should meet with this, or it should comply with these assumptions. It's something like you are going for a registration of your car, right? Car registration. Let's say you bought a new car, or you bought a used car. When you go for a registration, they need your ID proof, they need your address proof, and also they need RC book. And in addition to that, they need the FC, right? Whether the vehicle they have done FC. In addition to that, whether you have insurance copy or not, whether you have renewed the insurance or not. Likewise, based on the two factors alone, they don't decide you can own the car, you can drive the car, right? So to drive a car on a road, you need to have all these things. Similarly, not only the root mean squared or adjusted R squared is sufficient, we need to validate the assumption, these 5 assumptions. It's very simple to remember. So what is linearity? The relationship between independent and dependent variable. That's what we have seen it here. The relationship between the independent variable, dependent variable is linear, which means, 0.8 somewhat closer. This one is somewhat, very close to 1. These two are really good, but these two variables are not at all good. Hence, we can knock out this. We can only keep these two independent variables to train our model. In that case, what will happen is there exists a linearity between these two things. Okay. Next one is the independence. The residuals, the differences between the observed inputs should be independent of each other. The residuals is also called as a error. Okay, the residuals, the difference between actual and predicted values. That is what your residual. The residuals are error. Okay, it should be independent of each other. Should be independent of each other. And next one is the homoscedasticity. What is homoscedasticity? The variance of the error, variance of the residuals or errors should be constant across all levels of the independent variable, all levels of the independent variables. Next one is the normality of residuals. If you plot the errors, right, which is not residuals is nothing but the errors, okay? If you plot the errors, it should be normal, okay? The residuals should be approximately, okay, approximately normally distributed. No multicollinearity. Like I said, right? There should be a correlation exists between independent variable and dependent variable. Each independent variable should have a correlation between the independent dependent variable, but there should not be any correlation exists between the independent variable itself. If you see here Park and MISC, what happens here? Look here, if you see here, right, the Park and MISC, if you see here, the value is 1 here. That means, there is a perfect correlation. That means these two independent variable itself correlated. This is it is invalidating the assumptions. Okay, it is against the rule. But anyhow, since these two variables are not at all correlated with targetable, we dropped this one. Hence, we can say, hey, yeah, cool. So we don't have any multicollinearity. What is multicollinearity? If there are any relationship exists amongst the independent variable itself, that is against the rule. That is against the rule. See, it's something like a gay and gay, right? If they get married, it is something violating, right? It's kind of a, maybe it's a stupid example. Bear with me, okay? Two gays, right? It's something like, two people should not be same, right? Guy and guy should not get married. Okay, it's something like multicollinearity. Okay, but a guy and girl should marry, but they should have some perfect relationship, right? So not only the outlook, but also the other aspect, right? How good are they? How caring are they? Right? Something like that. Similarly, Mark and price can have a correlation. MISC and price can have correlation, but these two should not have correlation. Okay, it is against the rule. So how do I check whether the independent variables are correct? Using this heat map itself, we can find out. The other option is there are some functions are available using which we can find out. Okay, just give me a second. My batteries are running down. My laptop. Okay, now the question is how can I check it? All these things here. You can use the heat map, in this case, the linearity. The residual should be independent, right? So, okay, for this, we have some stats models. Apart from scalar, there is something called stats models package, using which also you can fit the model. Here, import stats models, so using which you can validate all the assumptions, because it has a lot of methods are available or functions are available, using which you can evaluate model performance. Okay, import SciPy, scientific Python. Import stats models dot stats dot stat tools. We can import other stats models dot stats as stats. Okay, enough. I just it's stats. Yeah, Soundra, you just watch what I'm doing it. Okay, and then I will answer it. Don't worry. Too early to explain. Wait. Here, I'm going to use. I'm going to fit the model. Okay, we have something called YLS, like linear regression class. Look here, in this case, SQL on itself, linear regression is available. But we have something called stats models. Okay, here I gave the short name for this package, smf.ols. OL is a function. Here we are going to specify formula is equivalent to, for example, my target variable is price. And then we need to use something called tilde, and all the independent variables you need to specify it on the right side of your tilde sign, UDS plus. Yeah, this is enough. Okay, and I'm going to say which data frame this data set is there. We need to tell it explicitly. Is equivalent to HDR. I'm going to say dot fit. Without fail, you need to say fit here. Okay, I'm going to execute this one to check. Yeah, there are no syntax error. Now what we will do is print. This gives you nice output lm dot sorry, print, lm dot summary function. So how many of you are aware of R language? There is something R language. Like R language, the lm dot summary function gives me the detailed information about your linear regression model. Here you can see R squared is also another metric, adjusted R squared, right? So adjusted R is always, most of the time it will be lesser than your R squared. Your adjusted R squared is 0.894. If the adjusted R squared is somewhat closer to 1, your model performance is really good. 89 is really good. 90, somewhat 90. It is close to 1. That means model performance really good. And apart from the F star, so many things are this. We'll discuss it later. Okay. So look here itself, we can see the intercept is this one. This for the size independent variable, the slope is this one. For the UDS, the slope is this one. And then it gives the standard everything. Okay, fine. Let it be there. Next one is we wanted to predict, we need to validate the model assumptions. What I am going to do is we want to check the independence of the model. Okay, here what I am going to do is I'm going to say we are some the Bruce-Pagan test. Okay, first we will do what we'll do is one, diagnose the autocorrelation. Are there any correlation exists between one error to another error? Okay, and then yeah, fine. So here to check this, we are conducting something like 1 second. Here I just give a bigger hash so that it will be titled very visible. Diagnose. Okay, spelling mistake. We'll correct it little later. Okay, here I'm going to say the independent test, right? So independent test or assumption 3 or something like that. And here assumption number 3, something like that. Okay, you give some name. Okay, SMS dot het Bruce BRUS Wagon, and here lm dot inside the function lm dot res id comma lm dot model dot exog. Okay. Here in this case, we need to use something like okay. I'm going to do this one again. I'm going to execute this one. Let us see if this ASM is not defined. Okay, I think you're not supposed to use this one. SMS is not defined. Okay. This is the one. Okay. What I am going to do is, in this case, I'm going to specify it as SMS. Okay. Here. SMF. Okay. This is okay. I'm going to say import stats models and formula dot API. This not stats dot API. Okay. We'll say stats dot API. I'm going to say SMS here. Okay. I think so. This is correct. Yes, it's correct. Now we will go and execute this one. We can see, this is the correlation value. We get some different values, right? 3.40, something like that. Okay, Bruce-Pagan test. And next one is, I will explain. Don't worry. Okay, let's go one by one. The next one is, the second one is we diagnose the multicollinearity. Collinearity. In this case, I'm just using some variance VIF, variance inflation factor. See, all these terms are, little bit different, but end of the day, it's all very simple. Okay. But if you talk to someone, hey, variance inflation factor, Bruce-Pagan test, people will look at you up and down. Oh man, this guy is a real scientist. Variance underscore inflation inflation underscore factor. Here I just say, the x dot values, comma I for, sorry guys, I got up with cold. I ate a lot of ice cream. Mm. I use the square bracket because we want to list comprehension. You remember list comprehension? We discussed about list comprehension. And I'm going to use VAR. I is not defined. Okay, for I in range, x dot okay, x dot shape. Okay, here. Oh, sorry, not I. It is 1, right? So 0 is rows and 1 is columns. The shape function gives you the rows and columns, right? Variation inflation factor is not defined. Okay. Variation inflation factor. I think this one is available in some function. I don't remember it. Just give me a second. Okay. This one is available in from stats models dot stats, and you have something called outliers. Okay, outliers underscore influence import variance inflation. I remember this function, but where to import? Just now I'm able to recollect. Okay, good. And I'm going to hit the run button. Yes, good. So if this is for the 2.35 is for our first variable size. Second one is for our UDS. You remember the for park and MIC, the last two independent variables, I removed it because there was no correlation exists between those two independent variables, dependent variable. Okay, after removing that, we are left with only two independent variables. One is the size and other one is UDS. For size, this is the value, and UDS. If you find any value which is greater than 10, okay, that means there is a correlation amongst the or between the independent variables. It's something like a guy likes a guy, right? That is not the correct thing. If you find 10 and above, that means you have some multicollinearity. But in this case, 2.35. Hence, each variables are independent. It is not correlated with each other. Very good. So in this case, it is adhering to the second assumption. Okay. Similarly, we have we need to make sure that the residuals are normal. For that, yeah, 1 second. We have another test called Kolmogorov Smirnov test. Okay, this test we can use it to find out whether the residuals are normal or not. Okay, here what I'm doing is import already SMS is there, right? Okay, fine. Stats dot KS test, Kolmogorov Smirnov test, LM dot res ID, comma nod. I don't know if this one is still available. KS test. Okay, like I suspected, it is not available now. I think they might have removed it. Okay, and let me do one thing. From SciPy, import stats. Yeah, we need to use this package here itself. So in this package, we can see we have stats thing, and along with it, we have Kolmogorov. So this is the function using which you can check whether the residuals are normally distributed or not. Here, the p-values, it ends with E minus 0. That means 0.0007. That means here the null hypothesis, it is not normally distributed. The residuals are not normally distributed. Since the p-value is less than alpha, we are rejecting the null hypothesis. We are going to convert the alternative hypothesis true. What is alternative hypothesis? Alternative hypothesis is your opposite of your null hypothesis. That is what we learned as part of hypothesis test. In this case, the null hypothesis is the residuals are not normally distributed. That's why I told you guys, if the p-value is less than alpha, we are going to simply reject the null hypothesis. This is a global rule, universal rule. You need to remember it. Here we have KS test. This function makes our life simple. All you need to just find out the residuals or the errors of this model, linear regression model. You just put it here. It automatically finds out the residual for each and every observation, and then whether it's a normal or something. That's all. It gives me the p-value. With p-value, we can quickly make out, yes, the p-value is less than alpha. Hence, we are rejecting the null hypothesis, and then we are going to conclude there are no, the residuals are normally distributed. Okay, normally distributed. So this one also meeting our the assumption, other assumption. We have this, residual supposed to be normally distributed. Yes, and in the independence of residuals, this one, Bruce-Pagan test, right? And then the homoscedasticity and multicollinearity we already tested it. There should not be any correlation between the variables, independent variables. Now the residuals are normal, and homoscedasticity is something like this. So for this, we use something called Durbin-Watson test. Okay, to check the 1 second. I will show you that one also here. Ideally, I will put it here. Okay, here I just say yes tools dot Durbin underscore Watson L number residual dot ID. Rest dot ID is nothing but it gives me the error. Okay, residuals are nothing but error. So this is the one, 2.07. This is the one I'm getting it now, right? So test statistics is 2.07. In this case, okay. I'll do one thing. I will use print statement. So what is this one? Durbin-Watson test. We use it to check, are there any homoscedasticities there in my data set? Even in this case, it gives me the test status 2.072. It's kind of your the test statistic value. If you wanted to know the this one, right, the p-value. I think you need to use it followed by the, this thing. You need to use something like p-value. There are different tests are available. Okay, p-value is not available here, right? Python history is there. Okay, let me do one thing. I press tab here, 1 second. If I press tab, and you need to wait, and here it's not giving me anything useful here. So or else, this is what we are testing it for homoscedasticity. Okay, here, otherwise what I'm going to do is plt dot scatter scatter plot. Okay, and here I'm going to do residuals. Sorry, predicted value, preds, right? Preds, comma, residuals. Using which residuals are nothing but errors, okay? The actual and predicted value. So now the preds one, you remember, if you scroll up, you can see that I applied this model on the training data set itself. That gives me the predicted value. And I'll just show you again. Model, and here what I did. Okay, here I did not put that one, right? Yeah, model X-train. Yes, spread one. Instead of spread one. Here I just put spread one. Guys, it's very simple, but you need to practice it. If you don't practice it, you will not be able to understand. And I'm going to click on it. Linear regression has no res ID. Model dot res ID should work. Okay, sorry. In this case, lm dot res ID. Let us, because we are using this one, right? Here I am using the stats function. That's why it got confused. Now I'm going to use predict function, right? Predict function, we have not used it on the in the stats model, which we used it. Okay, anyhow, let's not worry about that. Wait, I just show you with this itself. Because the res ID is not available as part of your model. Okay, that is the problem. In sklearn, there are some functions are not working. That is the problem. Ideally, they could have included everything there itself. What to do? So now I just say model dot, and here the residuals. You know, these guys, they did not include residuals. Okay, what I will do is here we have used the lm dot res ID, right? Yeah, the same thing I'm going. Let's use the same model here instead of using the previous one. Residuals. And here we need to plot this one, the predicted value. See, ideally, when you plot, listen very carefully. Very simple concept, but difficult to understand. This is your size. For example, area of your house. Okay, this is your predicted price. For the 500 square feet, you know very well, as the size increases, the price will also increase. The predicted price will also increase. You have some observations, you know, something like this. If you see something like this, is called your homoscedasticity. Homoscedasticity. That means, you know, as the size increases, the predicted value also increases. So, increases, more, right? So we know very well, as the size increases, the price also increases. But when you increase the price, when the predicted price, it should not be like the funnel kind of shape. You find something like funnel shape, it is called homoscedasticity. So in this case, actually, this is kind of error, right? Yeah, error. The error. As you increase the size, the error should not be more. Okay. The error should be something like this, right? Even if the size increases, what is the error? Error is the difference between actual and predicted. Okay, it's not price. Okay, it's error. It should be random, right? It should be something like that. It should be something like that. It should not be like a funnel shape. The error is more. See, for example, for 500 square feet, my model predicted price, the actual prices is 1 crore. The predicted value is let's 0.9 crore. Okay, somewhat close by. And let's say if the square feet increases to 1000 square feet, let's say this one is 1.8 crore, and 1000 square feet is, let's say, 2 crore. And if my model predicts something like 3 crore, as the size increases, in this case, what will happen? This is your actual and predicted, right? The predicted minus actual minus predicted, subtract, the difference is minus 1 crore. 1 crore difference is there. Okay, it should not be like this, right? As the size increases, the error should also be, somewhat random like this. It should not be like as the size increases, the error should also increase. If that increases, that means you have homoscedasticity. Okay, for that we need to use a res ID. Okay, and then so here what we do is so I'm just thinking how I can show you in this one the okay. Let's do one thing. Residuals is lm.resID. Is this working fine? Yes, this is working fine. Next, what I do is there is something called fitted values, okay? And I'm going to say predicted values, spread values. Here I'm going to say more my lm dot fitted values. Fitted values are predicted values for my training data set. What is the error? Okay, the actual and predicted value difference is that one. Next, I'm going to plot this one. Okay, plot scatter plot. Okay, instead of this one, predicted values, I'm going to say spread values and then the residuals. Okay, and I'm going to do this one. So here, as the size increases, it's kind of random. We don't see funnel shape, right? If something goes like this, funnel shape, then something wrong. Okay, your model is not predicting correctly. There is something wrong here. Okay, this is called your homoscedasticity. Visually, we have very homoscedasticity. Just because the housing price, the square feet increases, if the predicted value also very high, that means your error is more, right? Obviously, if your predicted value is way beyond your actual value, obviously the error will be more. Almost correct. This is number 3, right? So 1, 2, 3, and this is for the case using which we can find out whether residuals are normally distributed or not. On multicollinearity, we have seen it already, right? So almost all the assumptions are validated. So as per this, we can see that we don't see any correlation. The residuals are normally distributed, and almost we don't see any funnel kind of shape. Good, and we don't see any correlation between the independent variable itself. Good. And here the autocorrelation. Are there any correlation exists between independent and dependent variable? So here we can use this one, residual analysis. One second. In this case, autocorrelation, right? So what is correlation? Correlation is nothing but there should not be any correlation exists between the error itself. See here, I have written it, right? No autocorrelation. That means there should not be, if, for example, your actual price and predicted price, okay, and the error. Your actual price is 1 crore. The predicted price is, somewhat close to 1 crore. Error is 0. But here, 1.8 crore actual price. The predicted price is 1.7 crore. So the difference is 0.1 crore. Okay. but there should not be any correlation exists between these two error. Okay, just because this error is 0, this one has gone, something like that. Okay, there should not be any correlation between this. That is what this assumption tells us. No auto correlation. There should not be any correlation between the errors. Okay, this error, there should not be any correlation. Okay. So for that, we use the for that only we use the Durbin-Watson test. Okay, Durbin-Watson test. Where is the Durbin-Watson test? Here I have used the Durbin-Watson test. Sorry, not this one. Autocorrelation. For this we use SMS dot Bruchswagen. Sorry, heterogeneous. Bruchswagen, not Bruchswagen. Durbin-Watson. Durbin underscore Watson. That is for your autocorrelation. LM dot res ID. LM is your model name, linear regression model name. Okay. Okay, here I just delete this one. Let's see what this one gives. 2.072. Yeah, previously we were getting the same thing, right? Yeah, this is Kolmogorov. This is for normality. This for normality. This is for this purpose. Okay. And what I do is I just store it in a variable. This is called your autocorrelation AC. Okay, and AC dot something like that. Okay, let me do one thing. AC dot tab. Okay, this is not the p value. Ideally, if we get the p value, we can say, hey, this is the one, right? What we will do is I'm going to use. Okay, this one alone, I will just check and tell you. Okay, the Durbin-Watson test. How to I'm just checking my other code. You can use a function like this to do that. Using the test, when you conduct the test to validate the assumptions, you will get the p-value. If you get the p-value, that is enough. P, very well, if the p-value is less than alpha, alpha is there in our brain, right? So here, okay, here what I will do is SMS, right? Durbin-Watson is correct only. Model.res ID. Yeah. If the okay, in this case, how do we interpret this one? The interpretation is something. It's not the p-value here. Okay. If the statistics, okay, if the value, whatever the test statistic, okay, the test statistic is less than 1.5. That means positive correlation. If if the status is greater than 2.5, that means negative correlation. Finally, else. The else part, no significant autocorrelation. This is the logic, okay, pseudocode, okay. So here, okay, here what I do is I have stored it in this one, right? So what I'll do is I'll put use AC here. AC is the one holding that value, right? So here I just say print positive correlations of the problem, and else if AC negative correlation is also a problem. They should not, ideally the last one should get displayed here, okay. Ideally, these are the things should be mentioned inside the code, because print function requires a code, because these are not variables. This is unsolicited thing from Python, okay. And here we just say print no significant correlation. I just execute this. Okay, if not the, okay, this, that is for your understanding, I wrote it. 1.5, you need to specify colon here, right, in Python, yes. Where the body starts, okay, and elif, you need to specify this, and L spot also you need to specify. What is colon? After colon, you need to specify your body. Okay, this is your body. This is where your condition starts. Okay, the if block starts, if conditions block starts here for this, for elif the block starts here. For that you need to use colon. Okay, where the block starts, so no significant correlation. So it meets all the assumption. It is not violating any of the assumption. We can remove this one. Instead, Durbin-Watson test to diagnose the autocorrelation. We don't see any autocorrelation between the errors, and there are no correlation amongst the independent variable or between the independent variables. We don't see any funnel kind of pattern. Very good. And here the residuals are normal. Hence, it meets all our 5 assumptions: linearity, independence, homoscedasticity, normality of residuals, no or little, nothing. Very good. So our model meets all the assumptions. So in addition to the root mean squared error and adjusted R squared, we need to make sure that our model is meeting all these assumptions, or it is adhering to these assumptions. Okay, we need to validate that. But fortunately or unfortunately, in the sklearn, you cannot validate everything. So all the tests, right, that's all available as part of this set of packages. You don't have to worry about or memorize all these packages. Okay, I will just share the script. You need to execute it and then check. So tomorrow morning we'll make sure that the recorded videos will share, and also we'll walk you through where the scripts are available. Okay, not the tomorrow morning, tomorrow night. Okay, but you can watch the videos, and videos you can watch it tomorrow night. I will show you where I have uploaded all these scripts in our website. You need to download without fail, guys. Next weekend, we will practice